Okay, so today we would like to talk about chapter 6. Chapter 6, eigenvalues. Eigenvalues. Okay, so for linear transformation, we say that we could present the linear transformation as a matrix. So we focus on the matrix. And for the matrix, when we talk about matrix, eigenvalue is an important concept in the matrix. But however, we don't have too much time on the eigenvalue of the matrix of a matrix. But I think at least I will tell you some basic results. Okay. And so first of all, let's see what does it mean, eigenvalue. And when we say eigenvalue, it means that it's an eigenvalue of a matrix. It's an eigenvalue of a matrix. But what does it mean? Okay. So let me recall some well-known results or well-known examples. So now let's see the linear transformation R2 by R2. And if we define it by this way, the linear transformation we define by this way. And is send S1, is send this vector to. Sorry, I mean actually as we say, if it's a linear transformation, we always could figure out to find the standard representation matrix. Standard representation. It's standard representation A, right? And actually A is this one. L of 1, 0, L of 0, 1. In the first column, we can see L of 1, 0. In the second column, we can see L of 0, 1. And it's our standard representation. The matrix A is our standard representation. And for this matrix A, the first one, if the matrix A is this one, 2, 0, 0, 2. Then what's the product? AXY, what's this? It becomes 2, 0, 0, 2 multiplied by SY, their multiplication. So it's 2x plus 0 times 1, so it's 0. And the second 10, 0 times x plus 2y, so it's 2y. You could see that, right? And now both of them have the scalar 2. We could take out. So it's 2 times xy. 2 times xy. This one. And the vector xy is the vector, so I use the same bracket. This one. Okay, so here, if A is the form, and actually what's this? It's exactly 2 times identity. 2 times 1, 0, 0, 1, and 1, 0, 0, 1 is the identity. Then we can get A times any vector xy equals 2 times the vector xy. So for any xy, so for any vector xy in R2, AXY, or for any vector v in R2, AV equals, AV is actually A, this one we denote by V, and it's B, so this equation holds. AV equals 2V. If it's the scalar, the multiple of a scalar matrix, if it's a multiple of a scalar matrix, multiple of identity, and then of course it's scalar, multiple of identity matrix, then AV equals the scalar lambda times V. Here is lambda, and here is AV equals lambda times V. It's this one. Okay, but if and I will explain this one later. By using these examples, I will explain it. But now if A is it's not exactly multiple of identity, but it's still of the form, diagonal form. For example, 2, 0, 0, 3. Then what can we have? Now it's diagonal. Although it's not scalar multiple of identity. In this case, it's diagonal. It's also scalar multiple of identity. scalar multiple of identity, then it has a base form, this one. But for any v, here it holds for any v, But diagonal matrix, then what can we have? If the scalar are different, then when you consider AV, X, Y, what do we have? As Y, consider their multiplication. 2x plus 0 times y is 0. Okay, so we just have this term. 0 times x is 0, plus 3y. So it's this one, right? But they are, both of them are, they are not the same, so we could not take out. So we just have this one, right? So, but for this one, how could you, for this term, you also could view it this way. If we consider A10, just let x be 1, y be 0. In this case, we let x be 1, y be 0. What will we have? We will get it's equal to x equals 1, y equals 0. X equals 1, so it's 2. Y equals 0, so it's 0. And it's equal to 2, we could take out 2 times 1, 0. Right? So for this vector B1, if we denote by B1, it's equal to 2 times the same vector B1. Right? So we have this one. AB1 equals 2 times B1. Right? If V1 equal, and here V1 is 1, 0. And here V1 is 1, 0 vector. 1, 0 vector. And we still can consider another case. I mean, if we let x be 0, now we let x be 0. We let y be 1. What do we have? Now, A and the 0, 1, their multiplication becomes, let x be 0, y be 1. So it's 2 times 0 is 0. 3 times 1 is 3. So it's equal to 3 times 0, 1. 3 times 0, 1. Right? So for this equation, we have AB1 equals 2B1. But for this one, if we let x be 0, y be 1, and we denote it by V2. Then it's equal to 3 times V2. So we have this term. For this equation, we have this one. AV2 equals 3 times V2. And here V2 is 0, 1. So now we have this one. AV1 equals 2 times V1. V1 is this vector. AV2 equals 3 times V2. V2 is another vector. Okay, it's diagonal case, and the diagonal entries are different. If diagonal entries are the same, we have this case for any vector V. But if diagonal entry is different, then we have this one. Okay, so in this case, we will call it this one. If this equation holds, for the vector V1, AV1 equals some scalar lambda times V1. If the equation holds, we call it 2 is the eigenvalue. 2 is the eigenvalue of A. The scalar 2 is the eigenvalue of A. And then the vector V1 we call it eigenvector. Eigenvector of A. It's an eigenvector of A, and it belongs to the eigenvalue 2. Because now we have 2 eigenvalues here, right? We also have another scale eigenvalue, It's also another eigenvalue for the matrix A. It's also the eigenvalue of A. And it's also the eigenvector. So it's also the eigenvector of A. But they have different eigenvalues. They have different corresponding eigenvalues. For this eigenvector V1, this equation holds. So we call it eigenvector of A belongs to the eigenvalue 2. And for this one, it's the eigenvector of A belong to the eigenvalue 3. Belong to the eigenvalue 3. The eigenvector of A belong to the eigenvalue 3. Okay. And for this case, they just have the eigen. Of course, in this case, they just have the eigenvalue 2. The eigenvalue of A just have the eigenvalue. They just have this one. Just one, yeah. The eigenvalue 2, yeah. And if a matrix have the for the eigenvalue or eigenvector, they play an important role in matrix, yeah, in matrix. And they have some nice result. Probably we could introduce some. Yeah, they have some nice results. So it's important topic about eigenvalue, eigenvector is important topic. Yeah. So for the eigenvalue or eigenvector, you could view it this way. We have a here. We have it's something like we have a form. It's something like we have a form. Let me see. It's something like we have a form. And for the form, for this picture, we could run in, run out, run in, right? Run out, run in. So it's something like if we fix some picture, if we fix some vector v, we could run out or run in. We could multiply by some scalar to get their for the new vector is equal to AB1. The new vector is equal to AB1. So 2 times some vector is something like we multiply, we run in or run out, and the equation holds. And for different pictures, for different eigenvector, their multiple is different. Then for the multiple is something like the eigenvalue. Okay, I just say you could view it this way. Okay, so now let's see. Okay, so now I have given you the examples. Scalar multiple of identity or diagonal matrix. So now probably you will say, but if the matrix is not of the nice form, that is not diagonal, what can we say? If it's not diagonal, but if it also have some nice result, if it's of the form diagonalizable, if A is diagonalizable, and of course for any matrix A, we could talk about its eigenvalue. We could define its eigenvalue or eigenvector. We could define it. Yeah, we could define it. But we said if we could figure out the eigenvalue or eigenvector. But if the matrix A is of this one, I mean of something like this one, then it has nice form, it has nice result. So even it's not diagonal, if it's diagonalizable, they have some similar result. And of course I will tell you what does it mean. It's in section 6.3. It's a result in section 6.3. And actually diagonalizable means that I will tell you the detail, but here I could tell you diagonalizable means that A equals P D P inverse. And the P is some invertible matrix. P is just some invertible matrix. And the D is diagonal. And of course D is some diagonal matrix. The matrix D is some diagonal. Originally the matrix A is not diagonal, but we could find some invertible matrix such that A equals P D P inverse. And here the matrix D is diagonal. It's of something like this form. Yeah. And for this kind of matrix, it also has some similar result. And it's in section 6.3. Yeah, so in chapter 6, at least you should know the result in section 6.1. Now we will talk about the eigenvalue, eigenvector in section 6.1, and diagonalizable matrix A is in section 6.3. So first of all, we will talk about the material in section 6.1 and the section 6.3. And after that, I could give you the application in differential equation. Differential equation is the material in section 6.2. Yeah, and probably we don't have too much time, so at least, so I will teach the material by this way, following the process, the order. Okay, so now I will tell you the material in section 6.1. It's just the eigenvalue of matrix and the eigenvector of the matrix, and how to figure out the eigenvalue, eigenvector. How to figure out, if I give you a matrix A, how to figure out its eigenvalue, its eigenvector. It's the most important thing, it's the most basic thing in section 6.1. In section 6.1. Okay, so now I erase it. This equation, so this section 6.1, eigenvalues, eigenvector. First of all, let's see the definition. We have a matrix A in n by n, and we say this. We have the equation holds this form. So if we say a scalar lambda is an eigenvalue of A, what does it mean? It means that if there exists some scalar v which is non-zero, the vector v is the vector v. It could not be. It's non-zero. It could not be zero vector. It could not be zero vector. Otherwise, here any zero vector times any scalar, it must be zero. A times any zero vector, it must be zero. This equation always holds. So the vector v, it could not be zero. Such that this equation holds. AV equals lambda v. So the lambda eigenvalue, lambda is called eigenvalue of A. And then the vector v also calls v is called eigenvector. V is called eigenvector of A. But probably for the matrix A, they have two different eigenvalues. So eigenvector of A belonging to, you could say belong to the eigenvalue lambda. If you want to describe in more detail, you could say it's an eigenvector of A belonging to the eigenvalue lambda. And here we have the example. But we also could give you one more example. I could give you one more example to see what it means. And then later I will tell you how to figure out the eigenvalue of a matrix. So the example, we have a matrix A. Example 3, 2, 3, negative 2. We have vector. Probably you will say, how do I know this vector V? Actually, later I will tell you how to figure out this vector. if you see their product, AV1, AV, their product, you will see 3, 2, 3, negative 2, 2, 1. What's the product? 3 times 2, 6, plus 2 times 1, 2. And 3 times 2, 6. Subtract 2 times 1, subtract 2. So it's 8, 4. Right? 8, 4. And the vector 8, 4. What's the relationship? You need to multiply by 4, right? So it's 4 is equal to 4 times 2, 1. Equal to 4 times 2, 1. It's equal to 4 times 2, 1. And 2, 1 is the vector v. So it's equal to 2, 4 times 2, 1. The 2, 1 is the vector v. So it's 4 times v. 4 times v. So we have the equation AV equals 4v. Here v, the vector, is non-zero. It's non-zero. And the multiple is 4. The multiple is 4. The multiple is 4. So what does it mean? It means that 4 is the eigenvector of A, the matrix A. And V, the vector V is the eigenvalue. Sorry, 4 is the eigenvalue. 4 is the, since V is non-zero. Since V is non-zero. So 4 is the eigenvalue of A. 4 is the eigenvalue of the matrix A. And the vector V is the eigenvector of A belonging to the eigenvalue 4. Right? So what do we have? What can we say? We know that 4 is an eigenvalue of A. And 2, 1 is an eigenvector of A belonging to the eigenvalue 4. Belonging to the eigenvalue 4. And in the graph, what does it mean? You could view it this way. Here we have a vector v, as we say, it's something like for the vector v, we draw in or draw out. And now we multiply by 4, so we draw out, right? So it's 1, 2, 1, 2 here. Original is our vector v, it's 2, 1. It's 2, 1. The vector v is 2, 1. And if we can multiple, if 2, 1 is the eigenvector, then it means that when we consider AV, their product, it will be still in the line, still in the straight line. And in the straight line, its multiple is 4. The eigenvalue is 4, so it's 4. So it should be something like it's this one, 2, this one. Probably this one. This one. Okay. Maybe this one. Yeah. So it's this vector is 4 times 2, 1. So F4. The vector F4. Okay, originally the vector V is here, 2, 1. And then when you consider AV, their product times 4 times 2, 1. A4. The vector A4. Yeah, and in this case we call this vector V, it's an eigenvector of A and belonging to the eigenvalue 4. So 4 is the eigenvalue. 4 is the eigenvalue. And then now I have a question. The question is, if 2, 1 is the eigenvector of A belonging to 4, how about 4, 2? Is 4, 2 an eigen? The question is 4, 2 an eigenvector of A? Or 4, 2 and 2, 1, the vector 4, 2 and the vector 2, 1, we just multiply by 2, then we can get this one, right? So next, we can, if we multiply by -1, how about -2, -1? If -2, -1, the vector is also an eigenvector of A. How about this one? And it's true. And actually, if it's an eigenvector of A belonging to the eigenvalue 4, it's also an eigenvector. It's also an eigenvector. Why? The reason is that when you consider this vector, what's the matrix AB? If we denote by U, Oh, okay, we could use it directly. What's the product? What's their product? It's 3, 2, 3, negative 2. Of course, you could consider their multiplication directly, but what's the vector 4, 2? It's exactly 2 times 2, 1, right? So it's exactly multiplied by 2 times v1. 2 times the vector v1. Their inner product. This one. This one. This one. The vector is 2 times this one. But 2 is just a scalar. It's just a scalar, so we could take in right hand side or left hand side, that's fine. For example, we could write it this way. It's 3, 2, 3, negative 2 times 2, 1 times 2. Just multiply a scalar, right? And here, what's this? For this part, it's our A, it's our V. So AV equals 4V, right? So for this part, it becomes, for this part, it's our V. So this part is 4 times V. But right hand side we still have 2. Right hand side we still have 2. This one. This one. So what do we have? We can get is 4 times, here is 2V. 2V, sorry, it's 2V1. It's AV1. Let me see. It's our V. V this guy, so here, sorry, it's V. Yeah, it's V. And here, so it's 4 times 2V. 2V is actually 4, 2. 2V is actually 4, 2. V, since V is 2, 1. V is 2, 1. So 2V is 4, 2. This one. So indeed, we still have this equation. A times 4, 2. The vector 4, 2 equals 4 times the vector 4, 2. So originally we have this one. Originally we have this one. A times V1, 2, 1 equals 4 times 2, 1. Originally we have this equation. Now we still have this one. If we replace 2, 1 vector by 4, 2 vector, we still have this equation. A times 4, 2 equals 4 times 4, 2. 4, 2. Just for this vector, we multiply by 2. For this vector, we multiply by 2. This equation also holds. This equation also holds. Okay? I mean, this one we could derive. This equation also holds. Just if we multiply by 2 simultaneously, then we still have this equation. Since we use the multiplication of two matrices, their multiplication, we still have this one. And for this one, negative 2, negative 1 is the same. We still have A, the matrix A, negative 2, negative 1 is equal to A times negative 2, 1, the vector 2, 1 times negative 1. And A2, 1 equals 4 times 2, 1. And we still multiply by negative 1. So finally, we have 4 times negative 2, negative 1. So finally, we still have this one. A negative 2, negative 1 vector times equals 4 times negative 2, negative 1 vector. Okay, so if 2, 1 is an eigenvector of A belonging to eigenvalue 4, then 4, 2 is also an eigenvector. Negative 2, negative 1 is also an eigenvector. In other words, for the eigenvector, if it's an eigenvector, once you multiply by any scalar, it's also an eigenvector of A. It's also an eigenvector of A belonging to this eigenvalue. So now we could define the eigenspace. So indeed, we could define the eigenspace. Let me see what's the. Okay, so now indeed we could define this one. The eigenspace so we still have another one. I mean, we have the matrix A in n by n, and we say, let me see. If we connect the eigenvalue V AB equals lambda V. Okay, if lambda is an eigenvalue of A, then the set V, we connect all AB equals lambda V. We connect this set. And we say for this eigenvalue lambda 4, 2, 1 is an eigenvector. 2, 1 is an eigenvector. And of course we have not said, we don't know does it have another eigenvector, we don't know. But at least we know that we multiply by any scalar is also an eigenvector. So for this set, we call it eigenspace. Eigenspace of A belonging to the eigenvalue, belonging to eigenvalue lambda. It's the eigenspace of A belonging to the eigenvalue lambda. Okay, we combine all these vectors, and we combine all of them. Then it becomes a eigenspace. As we said, we could multiply by any scalar. And actually, we also could consider the addition. I mean, if the matrix A times 2, 1 equals 4 times 2, 1, and we have another vector, for example, 4, 2 equals 4 times 2, 4, 2. This one. Then when we consider the addition, A of 2, 1 vector plus 4, 2 vector. For the matrix multiplication, we could separate. A21 plus A42. Right? And the A21 is this one, 4 times 2, 1. A42 is this one, 4 times 2, 1. 4 times 4, 2. Let me see. Yeah, 4 times 4, 2. Then we could tell the common number 4. Then here is 2, 1 vector plus 4, 2 vector. This one. So we still have this form. A and is the new vector W equals 4 times the new vector W. So for the eigenvector, if it's a eigenvector, we multiply any scalar, it's also eigenvector. And for 2 eigenvector, we consider the sum is still eigenvector. So for the eigenvector, if we combine all the eigenvectors, it's an eigenspace. It's a space. Okay. So now our question is to figure out the eigenvector. How do I know? How do I choose this vector? How do I know this vector? How do I know this vector? So now I want to figure out this vector. So it's our question. How to find them? So before I answer this question, I should tell you we should check the note. Use the note. You will know how to get the eigenvalue and eigenvector. Okay. So the first one, if lambda is an eigenvalue of A, what can we say? If lambda is an eigenvalue, as we say, it will satisfy this equation. AV equals lambda V, and the vector V is non-zero. So it will satisfy this equation, so we could write it this way. It's our matrix A, it's the vector V equals lambda times the vector V. And you could view it this way. The scalar lambda, but you could view it this way. 0, 0. If it's just 2 by 2, okay. Even n by n, yeah, just n entries lambda. This one. It's true, right? This one. Lambda times V. AV equals lambda V. Lambda is a scalar. Let me see. Yeah, lambda is a scalar. So For the vector v, you could view it this way. It's just the 1, 0, 0, 1 times v. Any identity, okay, here you can see 1, 0, 0, 1 times xy, of course it's equal to xy, right? So it's easy to see, it's our v, it's our v. So the vector v you could write it this way. It's identity times v. And lambda times identity is exactly this way. So we have this one. For some lambda, for some non-zero lambda, for some non-zero v, for some non-zero v. For some non-zero v. But here, AV equals this matrix, 2 by 2 or n by n matrix. Then we could move it to left hand side. So A subtract, here this part is lambda times identity. So you move it to left hand side, you will see AV subtract lambda I times V equals 0. And V is non-zero. V is non-zero. Okay, it's a matrix. It's a matrix. So you could combine them. The matrix A subtract lambda I times the vector V. You could combine them. You could combine them. Equals 0, V non-zero, this one. And what does it mean? When you consider A subtract lambda I, you could find some vector V, non-zero vector V, such that this matrix times V is 0. This vector times V is 0. What does it mean? Actually, it means that A subtract lambda I is not invertible. Is not invertible. The reason is that if A subtract lambda I is invertible, if it's invertible, what does it mean? If it's invertible, we could, for this matrix, if it's invertible, we could multiply by its inverse. So we could multiply by its inverse. Right? But now the equation is A subtract lambda I of V equals 0. So for this equation, A subtract lambda I V equals 0. We multiply by its inverse in both sides. A subtract lambda I inverse times 0. So left hand side, you will get identity times V. Right hand side is A subtract lambda I, its inverse times 0. But any matrix multiplied by 0 vector, it must be 0. It must be 0. So you could get V, the vector V is 0. But V is non-zero, so it's a contradiction. It's a contradiction. So once we have this one, we could know that A subtract lambda is not invertible. It's not invertible. In other words, we could use the determinant to explain it. If A is not invertible, means that its determinant is 0. Its determinant is 0. Okay, so it's the most important thing. How to figure out the eigenvalue of A? Just consider A subtract lambda is determinant. For its determinant, we could figure out some lambda satisfy this equation. Some lambda satisfy the equation. Then the scalar lambda is what we want. It's the eigenvalue. It's the eigenvalue. Okay, it's the eigenvalue. Yeah. So okay. So here, just the explanation. So I erase it. And then now I write down the process and give you the examples. I write down the process and give you the examples. The process to solve eigenvalue problem. Eigenvalue problem. The process to solve eigenvalue problem. First one, to get the characteristic polynomial, we have some names. Characteristic polynomial. Anyway, so for this name, you don't need. Yeah, I think for this name you don't need to memorize this name, but you should know determinant A subtract lambda I. The characteristic polynomial. It means that determinant A subtract lambda I. It means that determinant A subtract lambda I. Get the determinant A subtract lambda I. Second step, solve the equation. Solve determinant a subtract lambda I equals 0. Solve this equation to get eigenvalue. Lambda 1, lambda 2, and here lambda k. Here is n by A is n by n matrix. But probably we have some multiple eigenvalue. So probably we have some multiple eigenvalue. So counting. So here it's counting. Multiplicity. The final step for any eigenvalue, vi, here I goes from 1 to k. We want to solve a subtract lambda I x equals 0. We solve this equation. To get, you see that? Okay. To get eigenspace. Get eigenspace. To get eigenspace, null space of A subtract lambda I and V in its null space. A subtract lambda I will give you an example. Here V is non-zero. Yeah, so I will give you an example, but for this result, for this one, here, null space A subtract lambda I is the solution set. Here is the null space of A subtract. It's called null space of A subtract lambda I. It's just the notation, so I remind you again. And here, the vector V belongs to its null space. The vector V belongs to its null space. We call it V is called eigenvalue. Eigenvalue of A. Eigenvector. Eigenvalue is lambda I, so it's eigenvector. Eigenvector of A belonging to the eigenvalue lambda. And here, the null space of A subtract lambda we also call it eigenspace.